of applause for Bipasha Chakraborty.
Hello, I'm Bipasha and I'm a particle physicist. So in next few minutes I will take you to the journey through the exciting world of particles. So famous scientist and astronomer Carl Sagan once said, if you wish to make an apple pie from scratch, you must first invent the universe. Well, at a first glance you might think it is an overstatement. But if you think very carefully, you will understand this statement reveals a scientific truth. For any scientific discovery, we first need to know the basic laws of nature. We need to understand the universe, and understanding the universe is not possible without understanding its tiniest building blocks. Those are elementary particles. Now the questions are, what are these elementary particles, how they behave, and how do we see them? Well, we can't see them. Not with the most powerful microscope we have on Earth, because they are as tiny respect to us as we are respect to our galaxy Milky Way. And remember, Milky Way has thousands of stars, billions of stars like Sun. So the elementary particles are very, very tiny. So physicists actually have to invent something very clever to detect them. And it's like this, a particle accelerator. So what physicists do there? They take particles, particle beams with very high speed, very high energy, they smash them together, then the particles actually break apart into their constituent subparticles. Those subparticles fly around in every direction. So if we have very powerful electronic detectors placed in those directions, they catch those subparticles, and that's how we know the subparticles are there. That's how particle discoveries are made. So particle physicists have come up with a very nice chart of all those elementary particles, and we call it a particle zoo. At least one of these particles you definitely know, it's electron, because every day you are using electronics, your smartphone, computers and everything. Here I am not going into very complicated thing, but the things to know is that the particles on the left hand side, the quarks, and in the middle the leptons are the matter particles. They form the matter. And the particles on the right hand side, the bosons, they are force mediator. Well, let's take a case of a football game. You are watching a football game. So footballers are passing footballs among themselves and they are moving around. And how they are exchanging the football, that actually governs the game. Exactly the case happens here. Quarks and leptons are the players. They are exchanging bosons among themselves. A boson is like a football. And how they are passing the bosons, which bosons they are passing, that actually creates the force among those quarks and leptons, tie them together to form matter. At this point, I would like to ask you to take a pause to appreciate how this entire universe can be deduced in terms of the small number of tiny particles and their antiparticles. Isn't it wonderful? Well, physicists 40 years ago also thought it is wonderful and this is the complete story, this is the dead end of physics and we don't have anything else to discover. But we are human beings, we are very curious, we don't stop questioning. And this is very good because it gives me the job. So, we have a lot more questions to answer, and this is one of them. Whatever matters I just discussed, the particles, they form only 5% matter energy of the universe. So we know about 5% of the total matter and energy in the universe. About 95% we have no clue. What are their constituent particles, how they come, how they are formed, we have no clue. So I would say the achievement is not really that we know 5% of the universe, but the achievement is we realize that we don't know 95% of the universe. So, and this 95% is a clear indication that our particle zoo is not complete. We have lot more particles, at least it is a hint that we have lot more particles than this, but the thing is that experiment couldn't measure any particle yet. We haven't found any sign of any particle in the experiment. So we are at the verge of complete cluelessness, where we think we have more particles which are necessary for understanding of the universe, but we couldn't see them in experiment. What do we do? Well, would you believe that here, probing the vacuum space, it rescues us? Would you believe that? At this point, I would like to ask my audience to please raise your hand if you think a vacuum space means an empty space, nothing. Please raise your hand. Okay, few hands are there. Before becoming a particle physicist, actually I used to think like the same way, that vacuum space is an empty space. But for particle physicists like us, vacuum is a lovely word. We really love this word because it's very useful, and it is not a free space. It's more like this. Lots of energies and lots of particle in it, like energy and particle C. And if you compare with a normal lake or normal waterfront, as normal water lake can have ripples and waves in it, this energy C, vacuum, can also have ripples and waves in it. That's called energy fluctuation. And this energy fluctuation creates particles fleetingly out of vacuum. They are very short-lived, and after very short life, they actually again disappear into the vacuum. This process happening, so vacuum has lots of particles, and those particles are around us. We don't see them, but they are there. This process is also, according to Einstein's theory of relativity, equal to mc squared. Energy can create matter and matter can create energy. And also this process doesn't violate Heisenberg's uncertainty principle. Now suppose that we have undiscovered particles which we don't know they are there, but they are in the vacuum if they exist. And we call it, let's say, particle X. So particle X is there. Now the question is, how do we detect them? Now let's say electron is going through the vacuum. Now electron is a very friendly particle. If it sees any particle around itself, it will try to talk to them, it will try to interact with them. So this electron tries to interact with particle X. This interaction alters the vacuum properties of this electron by a tiny amount. So if we do theoretical calculations, we actually find tiny discrepancies arising in the properties of this electron. And that's how we know the existence of particle X. So my job is to calculate this sort of discrepancies from theory. Fine, we live happily ever after, but how do we solve the theory? That's the question. You know that particle physics theories have a lot of equations. True, we do have equations, so we have to solve those equations. But the problem is that the equations I deal with, we have no mathematical way of solving that, absolutely no way. We have to think something more clever. Of course, we have something more clever, that's why I'm doing a PhD. So what we think, we take a box like this. And we think the whole universe is that box. And it's like a grid box, having grids, and you can imagine it, it's like more like Rubik's Cube. And all the events like energy fluctuation, particle creation, particle annihilation, everything happening within the box. We set the rules of the game, and the rules are the equations of my theory. We take this system and solve this system. So basically we are coming from an infinite continuous space to a finite discretized space, and that's why we can solve it on computer. So we do that. The challenges are how realistic box we can make, how realistic rules of the games we can make, and after the game is over, we get results, how do we translate it back to the real physical scenario. So lots of challenges, but that's good. I love challenges. So I took these challenges and I tried to calculate some corrections in this number. So this number is called gyromagnetic ratio, very complicated name, so we don't go in the name. But what is this number? This number is very important. Any quantum physics theory needs this number as its basic number. And you can see, that I try to make corrections here in the last digits, which I have marked in red, 1 in billion place, like thickness of my hair compared to a football ground. And this tiny correction reveals the existence of any new particles in the nature, new physics. So sitting on my chair in the office in front of a computer, I calculate a tiny number which actually is responsible for the behavior of this entire universe. Isn't that fascinating? And you know, we might not be able to actually understand the universe completely, but claiming ourselves as intelligent being is a shame if we don't try. Thank you.